In this video, we're going to be going over Newton's laws. So let's start off with the first law, the law of inertia. So for the first example, we have you are in a car as it turns right around a corner. You feel yourself pressed against the left car door. Use the idea of Newton's first law and inertia to explain this experience. So, according to Newton's first law of inertia, we know that an object in motion continues in a straight line unless acted on by an external force. So we're going around a corner and then we feel ourselves being pressed against the left wall. So when we know that when the car turns right, your body wants to keep moving because of the inertia. The inertia is what keeps you moving in a direction. But the car changes direction and it goes to the right. So relative to the car, it feels like you're being pushed left. But in reality, your body, it keeps moving straight. But the car turns right underneath you. And then the left door, it pushes you right to make you follow the curve. There is no outward force. It's just inertia. So, now for the second example, we have if an object is at rest, can you conclude that there are no forces acting on it? So, when it's at rest, the answer is going to be no. And this is because an object can be at rest with forces acting on it. One great example is us. Being at rest is something that is relative to something, to a reference frame. And then on Earth, we always have Fg acting on us downwards, 9.8 meters per second squared, always accelerating us downwards. But we're not moving because of normal force. So the forces can exist. They can just cancel out. Forces can cancel out, and it's in a state of equilibrium. So think your vertical forces are canceling out because you have normal force going up, and then you have the force of gravity that's going down, and that cancels out, and that's why you're standing still. And then think about a box that has stopped sliding on an incline. Like going upwards is the force of friction, and going downwards is its force of it's mg sine theta that's trying to pull it down, but they cancel out, so it's going to be at rest. They just cancel out. So we have, like, for example, a box on table, box on incline, you have Fn and Fg. So this is essentially your F net is going to equal to 0. So when there is 0 net force, this means object remains at rest. If a force is exerted on a body, is it possible for it to move with constant velocity, and why? The answer is yes. And this is if the net force is 0. So when the net force is 0, that means that it is going to continue, and nothing will change its acceleration. It's just going to stay the same unless something adds to it or slows it down. So if forces balance, nothing adds or subtracts from it. So if force is balanced, F net is equal to 0. Then your acceleration is equal to 0. So your velocity is going to stay constant because acceleration is equal to the change in velocity over time. So if there's no change in velocity, that means that it's going to be constant velocity. So for example, you can think of, or if you know that to contrast this, we know that if there is a single unbalanced force, then velocity changes. Which of the following objects below, if neither, is in equilibrium considering the force vectors shown? Explain why you know. If objects look nearly in equilibrium, assume that it is. Well, we know that equilibrium, the definition is that the F net is going to equal to 0. On the left box, we can see an up arrow and a down arrow. But we can see that the sizes, they're not the same. So that means it's not in equilibrium. Different sizes. Now on the right, we can see that we have a diagonal force, a horizontal force, and a downward force. So this is also not in equilibrium because it doesn't balance. They don't balance. We could also do this by doing vector addition, but here we can kind of eyeball it and know that it does not cancel out. Are the left and the right boxes speeding up, slowing down with constant speed, and or motionless? Explain how you know. Let's add another box here where it would be in equilibrium. FG, and we have FN here. So for this box, we could say that we have a net force. Our F net is going to equal to 0. So when F net is equal to 0, there's two cases. The first case is that the box is motionless. This means at rest. Or the second case is that it is moving at a constant speed because there is nothing to disrupt its velocity by changing acceleration. So now the right box, we can see this can either be in two cases. So the first case is that it is accelerating. This is because the F net does not equal to 0. Or the second case is that it's speeding up or changing, this is like a subtopic, speeding up or changing direction. A person pulls a 2 kilogram box to the right with an 11 Newton force. A 3 Newton force resists motion. What is the weight downward of the box F is equal to ma? So we know that the weight of the box is going to be equal to 2.0 kilograms. By using the weight formula, we know that the force of gravity is equal to the mass of the object times the gravitational constant that is accelerating it downwards, which is 9.8 meters per second squared. So we can write that, plugging in our numbers, we have a mass of 2 times 9.8, and this is going to approximately be 19.6, which is this is going to equal to 19.6. This is approximately 20 newtons, so we're going to say 20 newtons downward. Because the reason why this is going to be negative is because we defined our axes differently. Because you consider this negative 9.8 meters per second squared, but if you define this as downward, this is our definition of our coordinate system. So that means that downward is going to be positive, and that up is going to be negative, according to this. So it's important that you remember to define your coordinate system and label directions if you don't give sign. That is not consistent with the regular coordinate system. Now, draw arrows for all the forces acting on a 2 kilogram box resting on a flat surface. Label the arrows with the appropriate type of force and give its values in newtons. So for the weight, your weight is going to be equal to 20 newtons. Now your normal force is going to be equal to the weight because it's resting on a flat surface and it's resting. It's not falling through. It's not accelerating. There's no vertical acceleration. So it's going to equal to the weight. And the summation of the vertical forces is going to equal to 0 because it's at rest on top of the table. It's not falling through. So this is going to be Fn, and it's going to equal to 20 newtons too. Now, we have an applied force of an 11 newtons, and it's going to the right. So we can write that this applied force, Fa, is equal to 11 newtons. And then for our friction, we can write that it's going to be 3 newtons to the right. So our Ff is going to equal to 3 newtons. It's going to be smaller because our summation of Fx let's see, draw all the person pulls, it does not necessarily say that it's accelerating, that it has a constant velocity. So we can assume that it's not equals to 0. So we know that FA has to be greater than FF. That's important that you mark because of the fact that it's accelerating right. It's moving right. What is the net force on the box? Sum all force arrows on your body diagram above. So, in the horizontal direction, well, we can actually just assume that let's just say that it's moving right at a constant velocity to make the second question simpler. So our horizontal direction, we have that F net is equal to 11 minus C. This is actually for 11 minus 3, and that's equal to 8 newtons right. Our vertical forces cancel. It cancels because the upward force is going to equal to the downward force. Now, find the acceleration of the box as a result of this force. So actually, it wants us to find the acceleration, so it's not constant. It's just moving right at an acceleration. So we can use Newton's second law, which states that F is equal to ma. Rearranging A is equal to F over m. Plugging in 8 over 2.0 is equal to 4 meters per second squared. A 50-kilogram crate sits on the ground. You pull upward on it with a force of 600 newtons. What is the weight force of gravity on the crate? mg of the box. So this is 50 kilograms, and it goes up, and it's pulled upward with a force of 600 newtons. And you want to find you can draw Fg and also your weights. So now we know that m is equal to let's write that again. M is equal to 50.0 kilograms. F of your pull is 600 newtons up. Fg is equal to mass times gravity. Fg is equal to 50 times 9.8. That will equal to 490 newtons down. Draw the free body diagram showing the forces acting on the crate and label them. You have the weight 490 newtons downward, and your pulling force is 600 newtons up. And we know that since the pull is greater than the weight, the crate will lift off the ground. And because it's no longer in contact with the ground, that means there's no force of the ground that is pushing up on the box in order to keep it on the surface. Therefore, that we can say there is no normal force. What is the net force acting on the crate? Add all the x and y forces. So the forces we have can be split into upward. So our net upward forces, we can write (600 minus 490 newtons). That's going to be 110 newtons up. Now you can use Newton's second law which is F is equal to ma. A is equal to F over m. A is equal to 110 divided by 50.0. This is equal to 2.2 meters per second squared. So it's going to be 110 newtons up and 2.2 meters second squared as your acceleration. So, and when you do Newton's second law, this is going to be of the system. So it's important that you first take the force of the entire system, which is this. This is the force that you have to plug in order to get your A, which is your system acceleration. You sit down on a chair. This is for Newton's third law. You sit down on a chair. Describe the pair of third law forces acting in this case. When you're sitting on the chair, you push down on the chair. In addition, the chair pushes up on you. That's because the chair has to support your weight, and otherwise, if it wasn't pushing up on you, you wouldn't be sitting on the chair. You would be falling through the chair. The mass of the chair would just collapse, or it would break. So this means that they're equal and opposite forces. The chair is pushing up on you and you're pushing down on the chair to create your equilibrium position of sitting. So this is going to be a force pair. A force pair is the equal and opposite relationship. So Fu on chair is equal to negative F chair on U. And this is Newton's third law. A 7.0 kilogram bowling ball hits a 0.6 kilogram bowling pin. The pin accelerated at 40 meters per second squared. Calculate the force exerted by the ball on the pin. What does this make the force on the bowling ball? How did you figure this out? So, you know that the mass of the pin is equal to 0.60 kilograms, and the acceleration of the pin is equal to 40 meters per second squared. So we know that the force on the pin, we can use Newton's second law. F is equal to ma, simply 0.60 times 40. That is equal to 24 newtons. So the force of the ball on the pin is equal to 24 newtons. So therefore, the force on ball is equal to negative 24 newtons. The force F by ball on pin, and then the force on ball by pin is equal to negative 24 newtons. That's a better way of saying this. So your pair is 24 newtons, negative 24 newtons. What is the bowling ball's acceleration during this collision? So we know that the mass of the ball is equal to 7 kilograms. And we know that the F force on ball by the pin is equal to negative 24 newtons based on the coordinate system we have defined. So F is equal to ma, but we want the acceleration. So acceleration is equal to F over m. Acceleration, plugging in everything that's negative 24 divided by 7.0, that's equal to negative 3.43 meters per second squared. This negative means opposite motion. A 1,000 kilogram, an opposite motion means subtraction. Like you subtract it from your forces in the vertical or your forces in the horizontal direction. A 1,000 kilogram car starts from rest and its engine exerts a 4,000 newtons of force for 5 seconds. How fast will the car get? So we're going to use F equals ma, and we're going to use the acceleration in a kinematics equation. So we're given that the mass is 1,000 kilograms. The force is equal to 4,000 newtons. and your time is equal to 5.0 seconds. And we know that it starts from rest. So if it starts from rest, initially it had no velocity. So we can just write v initial is equal to 0. Now for the final speed, what we have to do is first find the acceleration. That's going to be 4,000. 4.0 meters per second squared. Now we use kinematics. So because we have a constant acceleration, we have v is equal to v initial plus acceleration times time. V is equal to 0 plus 4.0 times 5.0. V is equal to 20 meters per second. How far, which means find displacement, would the same car get in 5 seconds? So we know that x, your displacement, is equal to v initial times t plus 1/2 at squared. Initially, we know that the velocity is equal to 0. 0 times time, this is going to equal to 0. And that's going to be plus 1/2 of our acceleration, which was 4, times our time interval, which was 5 seconds. X is equal to 2 times 25, which will equal to 50 meters of displacement.